right. And we're up. Any questions? All right, then we last left off. We last left off with the EMF equal to the negative equal to the negative change in the magnetic flux with respect to time. I'm trying to remember, were either of you here for when I did this? Okay.
Are we still doing quiz today?
No, the stuff that you missed.
Sorry.
Today's the March 4th. Yeah, the quiz from March 4th and the test that was March 5th got shifted.
So okay, I didn't realize the quiz got shifted.
Yeah. Did you want to do the quiz right now?
It's fine, I'm fine with the new date. I just didn't realize.
Yeah. There was discussion last time was around that, about whether to do the quiz before spring break or after spring break. And the people who were here decided that taking the quiz just before the test would be better prep than doing it a week before the test. That was the decision.
I like how it's my time.
All right, so EMF is basically an ideal voltage. So if I have a battery or some sort of power supply with a 12-volt EMF, that is what the voltage is, but not necessarily what the effective voltage is. Because batteries have an internal resistance. In the textbook, they'll have a battery like this. Some of the problems in chapter whatever it is, 21. We'll set up a battery like this with a small little resistor to indicate the actual resistance. So the potential difference across here might be 12 volts, but across here would be less because the internal resistance is going to take away some of the, let's say, power. This is not really the right word. Some of the effectiveness of the battery. Now, the internal resistance of the battery is small. And it's going to get dwarfed by any other resistance for the most part in a circuit. And so that's why I tend to ignore it. This is the magnetic flux. It's the magnetic flux. It's just the electric field, or sorry, magnetic field times the area. So what we have excuse me. So we started out with Coulomb's law. From that, did a bunch of stuff, math and definitions, and came up with the sum of E dot A around it. A two-dimensional three-dimensional surface is equal to the enclosed charge over epsilon sub 9. This is Gauss's law of electricity. That's just Coulomb's law, a manipulated version of Coulomb's law. Then we had something similar for the magnetic flux through a closed surface. That's equal to 0. Blue markers will be fading. Gauss's law of magnetism. And the essence of this is, for Gauss's law of electricity, we can have an individual charge. I can have a positive charge, I can have a negative charge by itself, whereas for magnetism, if I have a north pole, I have a south pole. Although some physicists are looking for just a north pole or just a south pole. But if they find it, according to quantum physics, I can have a north pole that appears to be by itself, but it'll have some connection to a south pole somewhere else. We just won't be able to see the south pole. Then we get into Ampere's law. So if I look at the magnetic field around some length or some distance around an Amperian loop, that's going to be equal to mu naught times the enclosed current. And then we have that one over there, slightly different form. The electric field times the length is equal to negative change in magnetic flux. This is Ampere's law. This is generally called Faraday's law. And I'm going to throw in Lenz, Faraday and Lenz's law. From Ampere's law, we derived the magnetic field in the middle of a solenoid. Solenoid, just a bunch of loops of wire. Solenoid. Or a skinnier one. So from this one, we derived magnetic field through a solenoid in the center of the solenoid, U naught I, where mu naught is the permeability of free space. It is a constant. 4 pi times 10 to the negative 7th Tesla meters per ampere. N is the coil density, which is the number of coils per length. And I is the current running through the wire. And then from Faraday-Lentz's law, we established that the minus sign is indicating that it's going to create a magnetic field that will create a current that will be induced to oppose the change in the magnetic flux. I think that was worded badly. So that minus sign basically telling us no free energy. Nature doesn't like change. Write up one other bit, coulombs. Goes into that. All right, let's just do a quick example. All right, so basically I have a current here. Let's throw a switch into it. I'll put a switch there. So this is an open switch, and I'm drawing this badly. All right. When I throw the switch, we'll get a circuit, and I suddenly have current flowing through here. If I have current flowing through here, that means that I'm going to create a magnetic field. The magnetic field in the very center of this, as we talked about a few days ago, since if this is a circle of radius r, that the current, or the magnetic field in the middle is going to be mu naught times I over 2r. So the way I have this drawn, now it's a chance for you to show off. We're going to have a current flowing, first off, will the current flow clockwise or counterclockwise around this circle? Not a right hand rule, it's a power supply rule.
Clockwise.
Yes, and why?
I was just looking at the power supply, the larger one is where the power goes.
Or current?
Current.
Yeah,
Current.
absolutely. So from this, the current's going to be flowing this way, which means the current's going to be flowing around like that. So if the current is flowing clockwise, which way will the magnetic field in the middle go? This is a right hand.
Say that again. You're asking asking?
The magnetic field in the middle, which way will it be going?
Yeah.
Yes. Two ways of doing it. One, you put your thumb in the direction of the current flow and your fingers curl in the direction of the magnetic field flow, so it'd be in the middle, and out on the outside. Or you could also, the right hand rule also works with, if you put your fingers in the direction of the current flow, thumb points in the direction of the magnetic field flow for a circular circle. So the magnetic field is going into the center with that magnitude in the middle. It's not constant, but we'll use that as an approximation sometimes. Now, if I have a second wire, and that I have right here, second loop. If I flip the switch here, I go from no magnetic field to having a magnetic field. Since the magnetic field is changing here, that means the magnetic flux is changing. If the magnetic flux is changing, that means that I am producing an EMF in this wire right here, the red wire, a voltage, which means I'm going to get a current flow. So the question is, which way will the current flow in the red loop? Because the current in the red loop is going to create its own magnetic field. And the question is, will the induced current create a magnetic field in the same direction as the white magnetic field, or the opposite direction of the white magnetic field? This goes back to the no free energy, or the minus sign. Yeah. Since the magnetic field goes from nothing to suddenly going into the page, or into the board, the induced current will create a magnetic field that opposes that change. And so it will create a magnetic field that needs to go in the opposite direction to the initial magnetic field. And that will therefore create a current going clockwise. So put an I sub 2 there, because it's a secondary current. It's a current that's induced from the white current.
You mean it's going counterclockwise?
So the current would be flowing counterclockwise
Okay.
to create a magnetic field that opposes the gain of the white magnetic field. Just to let you know, Erica, my wife has COVID, so that's why I'm wearing a mask. I have no fever. Odds are she got it from me, which means I would have been contagious several days ago.
Oh,
However, there are masks here if you would like to wear a mask.
okay, thank you.
Now, if I open up the switch, my white current is going to drop off, which means the white magnetic field is going to drop off. Since the magnetic field is dropping off, I still have current flowing this way. Since my magnetic field is dropping off, which way will the current be induced in the red wire? Again, nature does not like change. Since the magnetic field is collapsing, the change is making B get smaller. So, since nature doesn't like change, am I going to create a secondary magnetic field that tries to bolster up the dying magnetic field, or one that will cause it to die faster.
Bolstered up.
Yeah. Again, nature doesn't like to change. So if my magnetic field, my white magnetic field is getting smaller, the current in the red wire is going to try to produce one to keep it from collapsing as quickly. So the current would be flowing in that case in the same direction as the external one. So the current, the secondary current, the induced current is going to create, try to do the opposite of whatever the magnetic flux is doing. If the magnetic flux is collapsing, it's going to try to make it stronger. If the magnetic field is getting stronger, the primary magnetic field is getting stronger, or, sorry, primary magnetic flux is getting bigger, it's going to try to make it smaller, and vice versa. Now, this was done with a single wire, or sorry, with two wires. Let's take a look at if I have only one wire. Get that yellow. If I connect the switch, I'm going to get current flowing clockwise around the loop. So we'll indicate that by, I close, that's not what I wanted. So if I close that loop, my current's going to be flowing like this. Because I am increasing the magnetic field in the middle into the board. So my magnetic field goes from